So our next speaker is Stephen Ward from the University of California, Santa Cruz, who will be speaking about Exodus, a geophysical perspective.
Is this back on? Yes, it is. Yeah. Well, I've got a pretty tough act to follow from the last speaker. Maybe I should call this geophysical imagination talk. Some of the speakers this week used the word wandering outsider, and that seems to fit me pretty well at this meeting. What could as I say, I'm a geophysicist, a seismologist actually. So what could a wandering seismologist help here? And there are a few things maybe. I'll be the first to admit that I know almost nothing about the Exodus story. From what I'm told, almost all of the Exodus escape versions involve the relative movement of land and water somehow. Water somehow aided the Hebrew people to escape and closed up on their enemies. I specialize in natural hazards. And not only studying them, but simulating them using a computer, using the physical laws. And the vast majority of natural hazards are just what you see here, the movement of land and water. So it seems to me that a geophysical perspective might have some bearing on the story, if not this story, some other story in archaeology. Whenever I hear someone talk about the movement of land and water, my ears perk up. And a geophysicist asks different questions than an archaeologist or a linguist. And my first question, when I hear about water moving, is, well, did the water go up or did the land go down? You might say it has the same net effect, but it makes a big difference if you're thinking about process. Processes that make water go up are very different than the processes that make land go down. And so you have to sort that out in your mind. Next thing for a geophysicist is a matter of sequence. How did things happen? In kind of the traditional view that you see in Hollywood, there was some wet area that dried up. People escaped through it, and then it got wet again, closed up on the enemies. From a geophysical perspective, that's very difficult to do. You have to move water from its equilibrium position, hold it backwards like a dam somehow for a period of time, and then release it. Aren't there many physical mechanisms that can do that? Maybe the sequence was dry, then wet, then dry again. That might have the same net effect on the story. People could escape through a dry area, and then it gets wet suddenly, and then dry again. That might be easier to do because it suggests something transient, maybe a wave or a flood. Or maybe the story was just dry then wet. People walked through some dry area, and then it got wet permanently. I could see a local earthquake. We've heard in the geological talk that there are possible faults in the area, a magnitude 6.5 earthquake. People are going through a swampy area or a sandbar, and an earthquake happens, the thing settles down, and an area that was dry turns wet. Perfectly reasonable to me. I put together 6 ways to move water and land that I kind of favor. They may have some application to the Nile Delta. We're going to go through these very quickly, about 2 minutes each, so if you yawn, you're going to miss one. I want to stress that I have no idea what happened at the Exodus. I have no idea if any of these are relevant or not. But I can pretty much assure you that these are going to be relevant to some other historic or archaeological site. So if they don't apply to the Exodus, they're going to apply to some other place you may be digging in the future or in the past. Let's start out with the earthquake tsunami. The Eastern Mediterranean does have sources of large earthquakes. The Cyprus Arc and the Hellenic Arc, home to magnitude 7s for sure, 7.5s, 8s. They could easily make a tsunami that would strike the Mediterranean and the Nile Delta. Let's try one. Let's put in a real earthquake using the real laws of physics and seismology that I know, and put one in. This is a big earthquake, probably the extreme that might possibly happen. 8.5 magnitude. And if you compute the wave all the way to Egypt, you get about 1 to 3 meters possibly. 1 to 3 meters if it's flat enough. We know that is quite flat. There are places below sea level, sand spits, lagoons. We heard about them several times. Could be it did something. I have no idea. An earthquake this big, though, would be felt widely throughout the whole Mediterranean. Would likely cause serious damage on Crete. So probably an earthquake that big would have been documented elsewhere or found in other archaeological sites on Crete. So something that big probably wouldn't have passed unnoticed elsewhere. How about volcano tsunamis? We heard about this in the last talk. Volcanoes do make tsunamis. Whether it affected Exodus, I don't know either, but they do. And the candidate that's been mentioned in the last talk and everywhere else is Thera. And from a geophysical perspective, Thera has a couple of advantages. One is an event that actually happened. It's not hypothetical, we didn't make it up, it really did happen. Two, it happened roughly in the same time period. So that's two pluses geophysically. We know volcanoes can collapse in lots of different ways, and there are certain ways that they do it that they can make very big tsunamis. No one knows for sure how Thera collapsed. My imagination of this, my geophysical imagination, as the last speaker would have it, I envision a big pyroclastic column being shot up a couple miles in the air, and after a few minutes it can't be supported by updrafts. It collapses down just like Krakatoa did, with the same mechanism. Transporting Krakatoa is not that bad of an idea, I think. It can make huge waves. 20 meters waves on Crete are not out of the question by this mechanism. So that's a geophysical plus. What's the downside from a geophysical perspective? Remember, these are all computer simulations using the laws of physics. I just don't draw these using MacDraw. The big downside is that there's not much open ocean between Santorini and the Nile. There's a couple little windows here. And that's very negative for tsunamis. You got to jam a wave through a little opening. Not much can get through for one. And when you jam the wave through a little opening, it's like a nozzle. It spreads out on the other side. So that again cuts down on the size of the wave. So maybe if you had a giant eruption at Thera, you can get again maybe 3 or 4 meters here, maybe. It would have to be a very huge eruption. It would send several dozen meter waves high to all the islands here. And there's been very few documented tsunami deposits. Some are pointed as tsunami deposits, but unequivocal. So that'd be another mystery. If a Thera wave got to the Nile, how come it's not seen so well in areas that are closer? How about landslides? Landslides are a very common mechanism to make tsunamis. It's quite possible. River deltas, like the Nile, are very good candidates for landslides. Sediment comes down, gets deposited when the water velocity decreases. Very common to oversteepen and slough off as landslides. If you go to the Mississippi Delta, there's lots of landslide scars in the past few thousand years. It seems perfectly plausible to me that such a landslide happened at the time of Exodus. You might ask me, well, where's this scar today? And again, from the geological talk, we saw that the delta is constantly changing. It was 50 kilometers back 4,000 years ago. Any scar that might have happened is long since covered up. There are landslide scars on this side that's a little less active in terms of sediment. Landslides can make a big wave underwater. How does it work? You take a big landslide, this one's maybe 70 meters thick, and you just shove it down into the deep ocean. And suddenly you have a 70-meter hole where land used to be 20, 30 kilometers across. Water tunnels into that hole, 70 meters deep, and it rebounds, and it spreads out. It's no problem at all to get a 5-meter wave over the Nile Delta. One interesting thing about a landslide origin is that the first thing you do is push the material down slope. You drop a hole in the water, and the first thing that reaches land is a negative wave. Water goes out first. So if you look carefully before the negative wave comes in, you'll see some red areas. Those are areas that were underwater but are now exposed. So if you're a fan of the wet, dry, wet sequence, this is one of the few ways. There's a dry land sea. And you'd have to be a coincidence. Like that last talk said, you just have to move fast. But there's one way to do it. One thing about landslides is you don't have to affect the whole Mediterranean basin. You could have a landslide happen, a tsunami just 20 or 30 miles across. That's a plus. You don't have to shake everybody up in the whole Mediterranean. I like that. What about wind? Wind's another possible way to move water around. You know how this happens. You get a bowl of soup and you blow on it and you push all the soup to one side, right? As long as you keep blowing, the soup will stay to the opposite side. As soon as you stop, it's going to come right back, and even more. Here's an example of a north wind. One of the great values of computer simulation is that you can actually put real parameters in and see how sensible that makes compared to things we observe elsewhere. How plausible is it, is the idea here. And of course, storm surge, hurricanes are the poster boy for this. We had Hurricane Sandy last year coming up to New York City. It was 3 meters of wave in New York Harbor just by blowing on the water. In this case, strong wind, 80 knots coming down here. So it's Hurricane 1 status. To get a wind-blown surge, you need two things. The wind has to blow for a long time, several hours, get the water going, and it has to be very strong. This may be 60 knots. So that's pretty strong. It's strong enough to blow Pharaoh's chariots away by themselves. So the wind hypothesis is going to require some extra coincidences, as the previous speaker said. Turn the winds to the south. We're going to, instead of blowing the water onshore, we're going to blow the water offshore. This is kind of cool. Blowing the water offshore exposes dry land again. Makes a depression offshore. When you shut off the wind, that depression fills up, just like the landslide tsunami, and the water rushes back. Because of inertia, it's going to overshoot and come roaring on the land. Another possibility for the wet, dry, wet scenario, if you like that. One of the things about winds is you don't necessarily blow the ocean, you can blow these little lakes. We've heard about the geography of Paleo Nile. Lagoons come and go, shallow swamps, sandbars, places that are below sea level. So you could easily blow a smaller lake, meter deep, and blow it dry. Probably can do it with less than 60 knot winds. So it's another possibility. This is one maybe you've never thought about. What about sabotage? Maybe this was a whole intentionally done. People were the same back then. They were smart. Geophysically, I kind of like the sabotage idea because the water already has its potential energy. It's already stored somewhere high. All you got to do is pull the cork on it at the right time. You think of it as something new, like the French underground blowing up the bridges in the war movies, but it's been around for a long time, especially the use of water. All you have to do is flood an area that's low already, turns into a mucky mess, and your pursuers are stuck for days. It's perfectly reasonable to me. So I could see the Hebrews helping their own cause. If they worked the land for generations, they would know where to set a trap. Why not? This might be the Nile or a storage river or one of those canals we saw from the Corona images. And I can see them kind of luring the army out, and they get out there and they pull the plug. And they get stuck out there for a couple of days. They make their escape. Doesn't require any miracles, just some thinking. Last one. I'm already done to my sixth one. Told you they're quick. Did you miss any? Flash flood. Flash floods are appealing geophysically, and other ways too, maybe. One, they're free geographically. You don't have to be near the ocean or near any river or lake. You can be anywhere in the Sinai and get a flash flood. That's good. Two, you don't need a widespread disaster. The previous speaker kind of ridiculed all these coincidences and big disasters. You don't need that. Don't need a volcanic explosion, magnitude 8 earthquake. You just need rain somewhere. And rains happen. Why do you think there's big basins here? Because they get flash floods that created the basin. The last big one was there in 1975. It made it rain so much that it put a delta at the end of this river here. The delta wore away in 2 years. So I can see a flash flood easily connecting to this story. Now, can you imagine that, say, Pharaoh's army is coming up one of these dry drainage rivers with banks on both sides, maybe trying to cut them off at the pass, what they say in the old cowboy movies. And suddenly it rains 50 miles away, and they're cutting this flood, and they can't get out. So you're stuck in a dry riverbed, and a 3-foot wall of water comes down. It'd be a mess. Here's a picture of a modern flood. I don't think it takes much imagination to visualize these cars as the Pharaoh's army. stuck and washed down and dumped on the delta. So I'm actually done already. My conclusions, it's just one. I don't know where or how or if water movements aided the escape of Hebrews from Egypt. But I'm going to claim that there are, from a geophysical perspective or geophysical imagination, I claim that there are plausible mechanisms. Thank you for listening. It's okay.
Yes, Tom.
Yeah, Steve, thank you very much for that. Steve, you helped collaborate with us. Hi, Tom Levy. I really enjoyed your talk, and you collaborated with us to do the scientific visualizations that we showed in the cyber archaeology exhibition, which was really about just showing how scientists can work with data, but as you pointed out, not to prove it, but it's a way of grappling with these natural factors in these ancient narratives. And I was wondering if you could say a few words. When we were working on this, Jessica Block from the Qualcomm Institute worked with us and you, and she reconfigured the North Sinai, the Delta coast based on Stanley's core evidence. Could you talk a little bit about how that worked with your model, with resolution and all of that?
Yes, well, most of these models were run on today's topography, but as you pointed out, the topography 4,000 years ago, about 50 kilometers of this area didn't exist. So when a wave comes onto land, it meets a lot of friction. There's things are growing, grasses, reeds. So if it can go over wetland, it can penetrate much further. So there is some differences in using older topography versus modern topography, but you have to imagine that for distant sources, by the time the wave gets here, the little details at the end aren't so important. It may be more important for the landslide model than the distant source model.
Yes, yes, please. Okay, the microphone is coming.
I'm something of a seafarer myself, and I'm wondering where are your water spouts, which are also
Where my what?
water spouts.
Water
where
spouts?
They fit into it?
You're trying to fish for more mechanisms, are we? That's okay. You mean like tornadoes over water? That's what you're talking about?
Yeah.
That's what a water spout is, as I understand.
And they can be extremely disastrous.
I don't know if they would move enough water. I mean,
That's the question I wanted.
tornadoes move pretty quickly. They suck up a little bit, but I don't think you're going to get
They're localized.
yeah.
They can be disastrous.
I don't think that's going to work.
Excuse me, I was.
Avi? Good.
Could you comment on exactly how a tsunami wave works with respect to transporting material? Because I see a lot of misunderstanding that a tsunami wave should carry a bunch of pumice with it toward a distant site, and I think that's important to clarify.
In the deep ocean, the wave just goes by with no effect on the seafloor. When the wave gets into shallow water, the motion at the top is identical to the motion at the bottom, and you really can bring a lot of material on. That's what brings sands and corals up to be deposited, to be recognized as tsunami deposits.
Right.
They also carry a lot of material off.
Right.
And some of these waves are 3 or 4 cycles, so much of the material gets on, 80% of it gets dragged back along with trees and people and rocks, and so there's a lot of movement of sediment on the beaches where tsunamis come in.
But in terms of pumice that originates from Thera, for example, would that actually move?
I see.
That's what I'm getting at.
The tsunami is going about 200 miles and 300 miles an hour here, so I don't think it's going to carry anything in the deep ocean, no.
I think there's some misunderstanding that if you find pumice on the coast, that it came from the eruption and it was transported at about the same time.
I doubt it, no. It was probably
Exactly.
brought by currents or winds.
And then I think you just alluded to the difference of your model if you had used the Bronze Age coastline, for example.
There can be some. It depends on the case by case. That's all you can say.
Thank you.
More? Yes, Thomas here. Okay.
Just one comment.
In a minute.
I'm not a supporter of the Exodus event, but just would like to make a suggestion that seems plausible. If there were such an event, we will have been looking here for extraordinary land and water movements, but the natural Nile inundation, of course, that happened every summer in Egypt is attested as having prevented foreign armies, for example, from invading Egypt. And that was a plannable event for anybody who would escape, right? So if the Nile Valley was flooded, the Delta was flooded, it was highly unlikely that troops could move. But
And once in a while there is a disastrous inundation also.
right, exactly right.
Yeah.
So I just want to mention that this is something that is very Egyptian and plannable.
But
Brad Sparks. Steve, could you comment on some of the scenarios for the Santorini Thera eruption and the magnitude of the tsunami waves at Thera, and then answer my question on your wet and dry scenarios. What
this is in the next lecture.
is going to be the next lecture?
Yeah.
Should we ask Amos?
Yeah, Amos will be
Okay,
speaking
okay,
about it in a minute, yes. Okay, thank you very much. Thanks a lot.